Hello and welcome to YMT211 Discrete Mathematics. We are still discussing Chapter 2. This is the last part of Chapter 2. We discussed two previous parts before about logic, the elementary part, concepts, the applications of propositions, compound statements, truth tables, and so on. So today we will learn how to use what we learned in the previous two parts of the chapter in something we call proof. So we prove what? We try to establish a sound procedure based on arguments, a valid argument or valid arguments to provide that a theorem is true or a statement is true. So we need to establish the truth or find the truth level or degree of a theorem. So what's a theorem anyway? Theorem is a statement that can be shown or proven to be true. Alright, how do we do that? How do we prove a theorem is true, or how can we show that it holds what it is assuming? We use usually what we call axioms. Axioms actually are statements that are assumed to be true. We don't show them, they are assumed already to be true. We use also the premises of theorem, relevant statements to the theorem that are also true, and also previously proven theorems. When we start establishing the valid arguments in the proof, we use things or theorems that are already proven. Otherwise, it's not that much easy to start from scratch and prove everything on your own. We have something we call a lemma. It's the less important theorem. It's a part of a theorem, you can say. It's a sort of a theorem, but usually less important than other theorems. Oh, why do we need it? Why do we use it? Usually in the proof also. Same like axioms, like premises. So we use those. Sometimes we establish another theorem or a sub-theorem from a theorem that's already proven. We call this theorem corollary in this case. It's a theorem directly established from a previously proven theorem. Okay. Sometimes we propose that some statements are true. It's a proposal. It may not be true. Okay, it's just a proposal. We propose that it's true based on our research, based on our assumptions, and so on. We call those conjecture. Okay, so these terminologies we provided here will be used later on within this chapter and other chapters in discrete mathematics. All right. Initially, we need to start with direct proofs. This is the easiest and the most forward way for proving in discrete mathematics relevant to logic. Now, direct proofs are based directly on what? On the essence of conditional statement. Conditional statement means what? The implication. P implies Q. Or if P, then Q. Alright, if you remember the truth table for this implication is what? It has only one case outcome, which is false, when a true is implying false. And in that case, the outcome here is false. Otherwise, it's always true. And that's why it is not hard to directly use it in proofs, and we call it direct proof. We assume that what we have here is irrelevant. What we need here is actually, what we assume here that's true, and if true is implying false, we need to avoid it. So we need to prove that this is true. Why? Because true implying false is always false, and we need to avoid that. Initially, we assume this is true. This is an assumption. Okay, assumption. And then we prove that the implied statement is also true. So true implies true is always true, and that's it. This is a direct proof. How do we do it? It depends on what kind of predicate or a statement that you are trying to show. Before we go ahead, let's take a definition, and this is a very essential definition. We will use it a lot in integers for different types of proofs. When we have an integer n, if it is even, then we can define it by this way. n equals to 2k, where k is also integer, an arbitrary integer, random integer that has whatever value, whatever integer. So when you multiply k by 2, no matter what the value of k, as long as it is integer, then the outcome here is even. This is the definition of even number, even integer. Right. And if n again is odd, then we can define it by k. The same k we assumed here, arbitrary integer number. It's an arbitrary integer number. It is equal to 2k plus 1. So again, 2k will get you an even number. Add to it 1 will get you an odd number. From integers, we speak about integers, and this is also important, so pay attention to this. We are considering integers here. Alright, let's go ahead and start some examples so that we see how we apply direct proof based on the conditions we provided. Now, give a direct proof that if m and n are both perfect squares, then n times m, or nn, is also a perfect square. Now, what's the definition of a perfect square? Perfect square, if you say a is a perfect square, then there is an integer b such that a is equal to b squared. In brief, what we need to do is we need to get something like this in our proof. A equals to b squared ultimately. Alright. It's not necessarily mn, but we need to get something squared. That's a perfect square in the outcome. So what is given? What's given here is m and n are both perfect squared. How do we define m? You can give it a value, m, let's say, equals to t squared, n equals to maybe s squared, and then. So we assume that this is true, this is true, both of them, and n and m. And then, based on the state that they are both true, we prove that the other side, then, the implied side, is also true. The multiplication of these two. So if we say m is, let's say, s squared, and n is t squared, then if we multiply s squared times t squared, that will be s squared t squared. So s squared t squared multiplied both in each other, multiplied times each other in the right hand side, and in that case, how can we prove that it is also true? Now let me show you. This is written here. S squared times t squared. It's easier for me to type with the mouse, it's a bit hard. Now in this case, what we need to do, it's simple actually. We need to just take the square because it can be distributed from both of them. It's like we multiply s 2 times ss, s times s, t times t, and that's exactly like squaring them both together. And this is what we want to prove. The definition of perfect square is a equals to b squared, and we got something like this, st, where we assume that m is equal to s, n is equal to t squared, so we got again squared here, and that's the proof. This is a direct proof, and it's usually easy and straightforward, and its application is similar to this. Now we have another proof. We call it the contraposition. Contraposition, it rings a bell actually. Why? Do you remember contrapositive? Also contrapositive, we spoke about the implication or the conditional statement. When we say P implies Q, if we say not Q implies not P, they are equivalent. They represent the same outcome. And this is what we call contrapositive, if you remember the statement. Alright, they represent the same outcome, and in this case, what we are looking for is a proof with what we call contrapositive. And sometimes it's not easy to go through the direct proof. We try the contrapositive to prove what's not easy to be proven using direct proofs. Now let's take an example. Prove that if n is an integer and 3n plus 2 is odd, then n is odd. Now think about the direct proof. What do we have? Now n is integer, okay, good. 3n plus 2 is odd. What's the definition of odd? 2k plus 1. So if we put 3n plus 2 equals 2k plus 1. Where will we reach? It's really hard to answer. Sorry about this typing, I'm just using my mouse. In this case, if you try to simplify, you will not get to an easy solution. So direct proof usually is tough. In this case, we won't get a quick or easy solution. And for this, what will we do? We will try the other way around. Now look, how will you diagnose a question and say, let's say, direct proof is not a good choice now? Look at this. You look at the implication, look at P and Q. Which one is simpler? P or Q? Of course Q is simpler. It's N, just N. Now look at this. Why I said this? Look at this. M, N. NM. So NM, we need to get N times M. Which one is simpler? Of course, M and N. So we go through the direct in this case. It's simpler, but here, which one is simpler? Is the implied statement N. How about if we take the other way around, contrapositive or contraposition? Contraposition says what? Not Q implies not P. Not Q, N is odd. If we negate it, N is not odd. Not odd means even, because in integers we have either even or odd. Alright, so N is even, not Q, implies not P. P is 3n plus 2 is odd. 3n plus 2 is even, is the negation of P. So not 3n plus 2 is odd means 3n plus 2 is even. So what do we need to prove? If n is even, then 3n plus 2 is even. It's easy. We can apply in this case a contraposition, and we can prove it in this way. N is even. How n is even is defined? 2k. We assume that an integer value k, arbitrary, random. So n equals to 2k. Substitute 3 times 2k plus 2. Now 3 times 2k, that's 6 plus 2, take 2 common. 2 times 3k plus 1. Now when we say 2 times anything, y, for example, this y, no matter what, as long as it is composed of an integer number somewhere, k, then it is even. Whatever you multiply by 2, if it is even or odd, composed of an integer number, then the outcome is even. And that's the proof. This is exactly the proof. So we have 2 multiplied by anything. It doesn't matter what it is. And in that case, you have got this proof. Meaning what? We went through the direct proof. It's a bit hard. We try to simplify things, and this is not easy. We try the contraposition. Contraposition, we say, well, okay, this looks simpler than this side. How about if we say not Q implies not P, which applies the contraposition in this case. Not Q means n is even. That implies 3n plus 2 is also even, because if we take the negation here, we need to take the negation of the other side as well. This is the contraposition, this is the conditioning. All right, in that case, n is even, it's defined by 2k, we just explained about it now. This is the definition by definition. Substitute, okay, 3 multiplied by 2k plus 2, take 2 common, then you will find 2 multiplied by something inside, which is composed of some number plus k. K is an integer. When you multiply any integer, even or odd, by 2, that's even all the time. And you got yourself a proof. All right, let's move on. We have another type which is very easy and straightforward of proofs. We call it vacuous and trivial proofs. And now remember that we have only one case. I said this at the beginning of my this video. What we have in the truth table of implication, we have only one false when we have a true is implying false. So here we have true implying false. This is the only case where the outcome is false, right? Okay. Now, how about false implying false is true? How about the rest of them? True implying true is true, okay? And in this case, how about false implying true is also true? So if it is false, if P is false, now false implying false is true, true implying true is true, but false also implying true is also true. Well, now think about it. False implying true is true, false implying false is true. How about the possibilities of P? P has two possibilities, either true or false. Good. When it is false, then no matter what Q is, the outcome is true. Think about the two conditions, the two states. When P is true, when P is false, we have two states for Q, either true or false, right? False implies true is true, false implies false is also true. That is what we call vacuous. Vacuous means what? If you prove that P is false, then no matter what Q is, the outcome is true. Why? In either way P, either way of Q, false or true, as long as P is false, then the outcome is true. Alright, go back to the truth table and check what I'm saying. Alright. Now in this case, we can have a proof for us. You can also apply the other way around. I'll show you in a while. Just let's take this possibility. Show the preposition P0 is true, where P, this is a predicate, okay? We have a predicate or a composition of predicates here. N greater than 1. If N is greater than 1, then what do we have? Now, if N is greater than 1, then N squared is also greater than N. We need to prove it. If we take this one and prove that it is false, then we have already proven that the whole statement is true, no matter what the value of this part, true or false, it doesn't matter. As long as this one is false, then the whole proposition is true. We are speaking about P0, substitute, so P of 0 here, and 1 is greater than 1 is not true directly. Sorry, 0 is greater than 1 is directly not true. So this is false. And once this one is proven false, then no matter what, this one is irrelevant. It doesn't matter. You have just to ignore it in this case. And that proves it. Once this first part is false, I don't care about the rest here. The implied statement, that part is irrelevant. And this is the concept of vacuous and trivial proof. Take the other way around. I will tell you about how we can take the other way around. Now let P and B, if A and B are positive integers, so A and B are assumed to be positive integers, with A greater than equal B, and A to power N is greater than or equal B to power N, where the domain consists of all non-negative integers. All non-negative integers means 0 plus the rest of positive integers 1, 2, 3. Show that P0 is true. So we care about P0. All right, substitute. Now let's substitute. If A is greater than equal B, then A to 0 or to power 0 is greater than equal B to power 0. All right, and in this case, anything to power 0 other than 0, of course, is 1. So except for 0 case, 0 to power 0 is something else. It has its own realm in mathematics, and we can say it's equal to 1. B to power 0 in this case is also 1. They are both equal to 1. All right, so now think about it. I cannot give this one true or false, right? I can't. It's not easy for me. I can say if it is false, I have the the vacuous or trivial definition of proof, but I can't. I'm not sure if A is greater than or less, or B is greater than or less, or whatever. I'm not sure, in other words, that this one is false. I don't know. Since I cannot prove it, how about if we check the other side? If this one is true, okay, if this one is true, then what does it mean? False implies true is true. False, true implies true is also true. And that's also part of this vacuous and trivial proof. If you can't prove the first part false, then prove the second part true. Okay? Look at the second part. A to power 0, is it greater than equal B to power 0? Yes. Why? Because both of them are equal to 1 in this case, particularly for P0, for P0. And the outcome is basically true here, the implied statement, and for that what we say is it holds. Once the implied statement is true, then no matter the implication at the beginning, the first part, false or true, is also true. Same as we said here, we ignore this one no matter what. As long as this part is false, then the whole statement is true. Now, no matter what, as long as this one is true, then the outcome is true. All right, let's take another strategy. This strategy is telling like a little proof. The little proof is stating that, okay, try with a direct proof. If you can't do it, then try with the contraposition and see if you can solve a problem or not. Let's take a direct example. For the direct example, let's say if we have n as an integer and n squared is odd, then n is odd. Now look at this. What we have here, n is an integer. All right. We have n squared is odd. All right. Now look, which one is simpler? N is odd or n squared is odd? Of course, n is odd is easier. If we go through the direct proof, it's really hard. N squared is odd is defined by 2k plus 1. And if you want to solve it, you will go to root plus minus, and that's difficult. The square root will not help you to simplify. How about if we take the contrapositive, or the contraposition in this case? The contrapositive says, if you say this is P, and this is Q, what you need to do is P implies Q can be replaced by not Q implies not P. Let's apply. Not Q means what? Not Q, n is odd, negated, n is even, implies not P, n square is even. So if we assume that we have an even number, n, then its square is also even. How can we do it? You can substitute n by 2k and then assume that this is true. So n is even equals to 2k. Then substitute 2k in n square and c. 2k all square will be 4k square. Or in other words, 2 times something here. Whatever it is, as long as it's composed of k, it will be ultimately an even number. Anything we said, the definition of an even number, 2 multiplying something which is integer, k squared, as long as k is an integer, its square is also integer with no problem. All right. And this is what we say, little proof strategy. Try with the direct proof. If you can't, go to the contraposition or contrapositive statement and try to prove. We have proofs for equivalence, Equivalence means what? Now we have biconditional, or the double implication or the double-sided implication when we say P if and only if Q, or P implies if P is true, then Q is true, and if Q is true, then P is Q. How do we represent them? Last video I explained to you about it. We say that P implies Q, and at the same time, and. At the same time, and. Okay, and. Also, Q implies P. All right, how do we prove if we have any statement like this? We go through it one by one. P implies Q, prove it. direct proof, contrapositive, whatever. Then you go to the second statement, Q implies P, and use whatever method, direct proof, contrapositive, vacuous, trivial, and trivial. It's up to you, totally up to you. Let's see, we have a direct example here. Prove the theorem if n is an integer, then n is odd if and only if, now if and only if, so this is double-sided, n squared is odd. Now n is even, n is odd, implies n squared is odd. Actually, we proved it, we just did here. Okay, we just did, but we did it with a contrapositive. But it doesn't matter, you can do it. You can assume n equals to 2k plus 1, substitute, and see how things go. It's not really hard, you can do it. All right, how about the other way around? N squared is odd implies n is odd. Which one is easier? N is odd. That take the contrapositive. Means the first one like this. First one, P n is odd, Q n squared is odd. N is odd, 2k. What's the definition of odd? 2k plus 1, assuming that k is an integer, arbitrary integer number. We can prove it. How about Q implies P, n squared is odd implies n is odd. Which one is easier? Well, n is simpler than n squared. Take the contrapositive. In order for you to do it, you can do it. It's not difficult. P implies Q, Q implies P. Take the contraposition, and you can get the outcome of this in this case. So it's not really hard. You can usually use different proofs to get to what you need based on which one is easier or which one is more straightforward. And we have a lot of applications. I'll create, as I promised, 2 tutorial sessions soon enough to have just discussion about examples for the past 2 chapters. And this is the end of this chapter. Until then, have a good time. Goodbye.